So most of this year we've been talking about relationships between variables x and y in the xy plane in rectangular coordinates. In the last 3 lectures we've talked about parametric equations and parametric representations, and we're going to kind of end up the year now talking about polar relationships, polar equations. So basically we're still in the xy plane, but instead of getting to a point by going over x and up y and getting to a point xy, what we're going to do to get to that same point is we're going to start with a ray on the x-axis here and come a certain number of degrees or radians, whatever angle measurement you want, up if you want to go positive, so counterclockwise, and clockwise if you want to go a negative angle. Just like x's to the positive are to the right of the origin and to the left are negative. And once you get an angle, then you're going to go out a directed distance, which we call r. So the angle is theta, and then you're going to go out r. And r is positive if you go from the origin, or as it's called in polar, the pole. The directed distance is positive if you go in the same way as the angle, and if you go the opposite direction, then it would be negative. So just as an example, say this was the point 1, 1. So this is 1 and this is 1. You could get to that same point by going 45 degrees out and then going out the square root of 2. So r would be the square root of 2, and the angle would be pi over 4. Now, because of the nature of polar, you could also go 5 pi over 4, which would head you in this direction, but then just go negative the square root of 2. So negative the square root of 2, 5 pi over 4 would get you to the same place. And because the angles keep going around, you could go to 9 pi over 4. Square root of 2, 9 pi over 4 would still get you to the same place. So anyway, that's just a little bit about polar. Most of you have been introduced to polar before. But there's a nice relationship that's really important. And if you ever forget it, it comes right from this little picture. What do we see? This is y, and this is x, and you've got a right triangle. So the sine of theta is y over r. So y equals r sine of theta, and x equals r cosine of theta. Those are important relationships if you want to go back and forth between polar and rectangular. And we see, since it's Pythagorean theorem holds, that x squared plus y squared equals r squared. So you can write, not only can you get points represented in polar, but you can write polar equations for figures. And some of them are efficient and some of them aren't. Like for a circle, x squared plus y squared equals 9. Since x squared plus y squared is r squared, we could write r squared equals 9 or just r equals 3. Much more efficient. But if you wanted to write a straight line like 2x plus y equals 8, now you'd have to go r cosine of theta plus r sine of theta. So it's not as nice for straight lines. Okay, so we'll talk a little bit more about graphing and that as we actually do calculus. So I want to get right into the calculus of polar. And today we're just going to concentrate on area. So just as a quick review, and this is always a good thing to do because it's such an important concept. In rectangular, if we wanted to find the area between y equals f of x and the x-axis between x equals a and x equals b, you've seen me do it so many times. We divide that up into n sections, and then we take this kth section and you make rectangles. And the height of that rectangle, you could call it y, or you could call it f of x sub k. In the width, we call this delta x sub k. So the area of that rectangle was f of x sub k delta x sub k. And then we added up all n of them, but we had that little bit of error, so we took the limit as n approaches infinity. And then we were able to get that exact area. Well, this turned out to be kind of a complicated process, but luckily we found out there was a way of finding that out much easier. We called that relationship the integral of f of x dx, or if you want, y dx, and found that there was a shortcut way of finding this infinite Riemann sum. You could just take the antiderivatives of f and plug in the two endpoints and subtract. So, quick review. Now what are we going to have? Still in the xy plane, we're going to have a representation in terms of r and theta. So you might have some function like that where r is a function of theta. Instead of y being a function of x, we have r as a function of theta. And instead of going from x equals a to x equals b, we're going to go from theta equals alpha to theta equals beta. And we're going to want to know the area inside here. We're going to do it in a very similar way. We're going to divide this up into n little slices, sort of like slices of pie. And so we're going to call this theta sub 0, theta sub 1, up to theta sub n, but then we're going to have this representative slice right here, which is going to go from theta sub k minus 1 to theta sub k. And we're going to call the change between those two angles right here delta theta sub k. And then what's the distance out here? That is r, so that's going to be f of theta sub k. Now the question is, this is not a rectangle, so what's the area of this slice? Well, it's going to depend on r and theta. So if you remember, if you have a circle, and that's theta, and this is r, we've got a total area of pi r squared, and what fraction of that do we have? We have theta over 2 pi. So you get 1/2 theta r squared to get the area of that. So in this case, we have 1/2 theta sub k, but it's actually going to be delta theta sub k times r squared. And r is going to be f of theta sub k squared. And we're going to do the same thing. We've got n of them, so we're going to add them up from k equals 1 to n. But because these radii aren't going to be exactly the same, it's not exactly coming from a circle. So you don't have a sector of a circle. So to make it so it is, we're just going to make these infinitely skinny. so the radii don't change, just like we didn't have the heights change over here. So we're just going to take the limit as n approaches infinity. And that's going to give us the area that we're looking for. But we're wondering, that looks really complicated. Is there a way I can do this and make it look like this? Well, it really is. You've got the limit as n approaches infinity. You've got the summation, k equals 1 to n, 1/2 f of theta sub k squared delta theta sub k. So the only real difference is, instead of x, we have theta, and instead of f of x sub k, we have 1/2 of f of theta sub k squared. So this is definitely in the form of an infinite Riemann sum, so we can write it as an integral. The integral of 1/2 f of theta squared d theta. And you're going from theta equals alpha to theta equals beta. And because f of theta makes it look a little more complicated and f of theta is r, normally you see it like this. And we can bring the 1/2 out front, r squared d theta. So this corresponds to this. So it really isn't that much different. What did we always need before? We needed a height, and the width was always dx. Now what are we going to need? We're going to need a radius. And theta is just going to be the angle. So let's get into some examples. And I'm picking some easy examples at the beginning to see if this makes sense. So what does r equals 2 look like? You could think of it as just for every angle theta, there's no theta in here, every angle theta, r is 2. So you're just going out 2 in every direction to get a point. 2 in this direction, 2 in this direction, 2 in this direction, 2 in this direction, and you see it would be a circle. Another way of looking at it is r is, well, you could square this and get r squared equals 4, so you have x squared plus y squared equals 4. In any case, you've got that circle. Now, whenever I've found areas in rectangular, I always drew in my rectangle. What I'm going to do now is draw in my slice of pie. So there it is. And where do those slices of pie go from? Well, you want to get this entire circle. So when you made that circle, it went all the way around from 0 to 2 pi. That's where all my angles went to. So first, you write your formula. That's always what we're going to do when we have polar, if we only have one equation anyway. And then what's r? R happens to be 2. And the angle that you made the pies from went from 0 to 2 pi. So altogether, you have 4 times a half. I can just leave the half out there if I want. The antiderivative of 4 is 4 theta. And altogether, I get 8 pi divided by 2, or 4 pi. What's another way I could have found that area? Pi r squared. Yes, that would have been a little bit easier, but this gives us some confidence in this new formula that we developed. So, let's get another curve. R equals the sine of theta. Well, one way you can plot is just to throw in some values of theta. So when theta is 0, you get r to be 0. When theta is pi over 2, you get r to be 1. And then when theta is pi, you're back to 0 again. But it's not going to just go straight up and down between those 2 points. When r is pi over 6, when theta is pi over 6, r is going to be 1/2. So if you went over pi over 6, you'd go over 1/2. And if you plotted all those points, you'd end up with something that looks like this. And again, what could you do up here to do the same thing? You could say that r squared equals r sine of theta. You could just multiply both sides by r and then say x squared plus y squared equals, and r sine of theta is y. And you could complete the square and get x squared plus, and then you have y minus 1/2 squared equals 1/4, and you get a radius of 1/2 and a center of 0 1/2. So anyway, now we want to find the area of that. Well, you have to be careful. You don't want to go 0 to 360. We made this whole thing by going from 0 to pi. All the slices of pi we made were made by going just the angles 0 through pi. So I'm going to use this space over here. It's 1/2 r squared d theta. And what's r? R is the sine of theta, and we're going from 0 to pi. Now, sine squared of theta. If you remember, for sine squared of theta, we have to go 1 minus the cosine of 2 theta divided by 2, which I could bring out front. Actually, I haven't taken the integral yet. I'm just using the trig identity to make sine squared of theta 1 minus the cosine of 2 theta over 2. And now I take the antiderivative of 1 d theta, and I get theta, and cosine of 2 theta is sine of 2 theta divided by 2. So altogether, if I plug in, I get theta minus the sine of 2 theta, which is 0. And when I put in 0, I get 0 minus 0. Altogether, I get pi over 4. Again, this is a circle with a radius 1/2. So the area would be pi times 1/2 squared, or pi over 4. So we're developing some confidence in this formula that we've got. Okay, well, let's try something different here. R equals 4 sine of 2 theta. I don't know what that one looks like, but let's plot some points. When I get 0 for theta, I get 0 for r. When I get pi over 2 for theta, which is up this direction, I get the sine of pi, which is again 0. So I have to look at some angles in between. Well, look what happens when I do pi over 4. When I plug in pi over 4, I get 4. And that's the biggest the sine is going to get. So I go out 1, 2, 3, 4, and get that point. And if you plotted some more, you'd get something like that. And you made all these going from 0 to pi over 2. This is important to know. As you're tracing this out, what angles did you go through? Well, if you went to 3 pi over 4, you get the sine of 3 pi over 2. So here's 3 pi over 4 in that direction, but we get a negative 4. So actually we're going down here. So what's going to happen is after you've traced this first loop, you're going to go down and trace another loop. Because by the time you get to pi, you're back down to 0 again. And another way of looking at it is you could say the sine of 2 theta is 2 sine of theta cosine of theta. So anything in polar where you have the sine of theta and the cosine of theta, the sine of theta makes it symmetrical with respect to the y-axis and the cosine with respect to the x-axis. And if you kept tracing, you'd see that symmetry. You get it? Oops. It would look a little more symmetrical than that. But this is what is termed a 4-leaf rose. And it takes all 0 to 2 pi to trace that entire rose. Now you can use the fact that it really is symmetric and only do from 0 to pi over 2 and multiply by 4. But since we did trace the whole thing, let's do it. So we went 1/2 the integral from 0 to 2 pi of r squared d theta. So we have 4 sine of 2 theta. So 4 squared is 16, so you have 8. And you have sine squared. So similar, again, we have to go 1 minus the cosine of 4 theta divided by 2. So the antiderivative is theta minus the sine of 4 theta over 4 from 0 to 2 pi. So you get 2 pi, and the sine of 8 pi is 0. And when you plug in 0, you get 0. So altogether, the area inside all 4 leaves of that 4-leaf rose will be 8 pi square units. Now, something to be careful for is that you can, in polar, you could get places like this that were really traced at angles not even between pi over 2 and pi. They might have come from angles down here that went back. So you do have to be somewhat careful to see where all these points are, what angles you were going through while you were tracing them. Okay, so let's do 2 more. Now we're going to involve 2 different polar equations and how they intersect. And I'm going to emphasize something of importance, and that is when you're making your sketches, even more so than in rectangular, make your sketches big, because seeing what's going on in these intersections is going to be important. So, r equals 3 cosine of theta. What does that look like? I think, if you remember, we hit on the previous board, we did r equals sine of theta and we got a circle. I bet you cosine of theta is going to be similar, because if I multiply both sides by r, I get r squared equals 3r cosine of theta. So that's going to be x squared plus y squared. It's going to have an x in it. So it is going to be a circle. Let's see. When theta is 0, I get 3. When theta is pi over 2, I get 0. And when theta is pi, I get negative 3. So pi goes out in this direction, but I'm going -3, so I'm back here again. So the circle, and this is where you want to take time to draw this neatly, if you can. So you're going to have a radius of 3, and then it's going to come back the same thing on the other side. That wasn't the greatest in the world, but let's see if I can just fix that up a little bit up in that corner. Okay, so there's my circle. Now, over here, I have something else. So when theta is 0, I get 1 plus 1 is 2. And when theta is pi over 2, I get 1. So I'm kind of going, and it's really going to be important where they intersect. So before I go any further, I'm going to set these two things equal to each other. And I get 2 cosine of theta equals 1, or cosine of theta equals 1/2. So theta is going to be at pi over 3, and also at negative pi over 3. So if I draw in pi over 3 and negative pi over 3, now I know where it's going to intersect. It's going to intersect right here and right here. And then, so I know I'm going to go like this, and then start going down, and then when theta gets to be pi, I have 1 minus 1, I'm back down to 0. So I'm back down to the pole, or the origin. And because this is cosine, it's going to be symmetrical. So it's going to do the same thing here and down here. It's symmetrical with respect to the x-axis. So I think it's worth your time to try to get a good sketch. So what am I looking for? Inside the circle and outside, what does that look like? A heart. So that's called a cardioid. So what we're looking for is this area right in there. So I'm going to draw in my slice of pie. My slice of pie is going to look like that. And what is the pie made up of? It's made up of this big slice in the circle, but then you're subtracting out that little slice here. So what we have to do is go pi one radius squared d theta minus pi, not pi, 1/2, forgot my formula there. It's 1/2 r squared d theta. So what is my big slice of pie came from the circle. So that's going to be 3 cosine of theta. And the little slice of pie that you're subtracting out came from the cardioid. 1 plus cosine of theta. Now the nature of these, when you have two like this, is everything is the same angles, so you can put them together into one. Right from the beginning. So I could have said big R squared minus little r squared d theta right at the beginning. And what angles am I going from? Negative pi over 3 to pi over 3. That's why it's a good idea to put in those rays to see where they intersect. There's going to be no pi past pi over 3 or past negative pi over 3. So I can just go from negative pi over 3 to pi over 3. Now, because of the symmetry, to save yourself some time, you can just multiply by 2 and go from 0. Just go this part of the pi. So if I put it all together, what do I have? 9 cosine squared of theta minus, and then I have 1 plus 2 cosine of theta plus cosine squared of theta. All times d theta. So 9 minus 1 is 8 cosine squared of theta. Then you have minus 2 cosine of theta and minus 1. Now the trouble is you've got cosine squared of theta. To make that, you're going to have to go 8 times 1 plus the cosine of 2 theta, all divided by 2. Or 4 plus 4 cosine of 2 theta. So if I put it all together, 4 minus 1 is 3 plus 4 cosine of 2 theta minus 2 cosine of theta. Okay, so now you're going to take the integral of that from 0 to pi over 3 d theta. So you get 3 theta plus 4 sine of 2 theta over 2. So 2 sine of 2 theta, and then minus 2 sine of theta. And you're going from 0 to pi over 3. Well, 0 is going to give you nothing. Sine of 0, sine of 0, 0. But how about pi over 3? 3 times pi over 3 is pi plus the sine of 2 pi over 3. 2 times the square root of 3 over 2 minus 2 times the sine of pi over 3. Same thing. The sine of 2 pi over 3 is the same as the sine of pi over 3, so you're left with just pi. So the area in this moon-shaped section is pi square units. Now, that's the last integral I'm going to actually take, but I want to show you another way you could set this up, because some of you might think of this differently. So consider taking this whole circle right here. That we can do with geometry. It's a circle with a radius of 1.5, because this is 3 all the way together. So I could go pi times 3 halves squared. Now, what do I have to subtract out of that to get this moon? I have to subtract out this area in here and this little area right up here. Now you can see the importance of having a good graph. So when we're doing this first area that I put in here, we're really talking about this pi right in here, which only goes to the cardioid. And I'm going to go from 0 to pi over 3 for those slices of pie. So I have to subtract those out of the circle. So minus 1/2 from 0 to pi over 3 of r squared d theta. In this case, it's the cardioid. So it's 1 plus the cosine of theta. But then you also have to subtract this area right in here. And now your slices of pie are only going to go to the black circle. So I have to go minus 1/2 the integral of 3 cosine of theta squared d theta. And here you're going from pi over 3 to pi over 2. When you're making your slices of pie in this little section here, you're starting at pi over 3. So anyway, either one of those two is correct. I'm not going to go through and show you that you get the same answer because the idea is not to learn how to do antiderivatives today. Okay, so one other thing before I leave this. I went from negative pi over 3 to pi over 3. That's important because when we're doing definite integrals, if we're going to use the fundamental theorem of calculus, we want to go from a lower number to a higher number and get all those angles in between. If I called this 5 pi over 3 and went from 5 pi over 3 to pi over 3, it wouldn't go in this direction. It would go from a smaller number to the larger number. So it would actually go this way, and you wouldn't get the slices of pie you're looking for. So there's certain things you have to be careful for in polar. Okay, so one more. Find the area inside r equals 2. I think we've done this one before. R equals 2 is a circle with a radius of 2. And then I'm going to try some values here. When I put in 0, I get 2. When I put in pi over 2, I get 0. And when I put in pi, I'm back down to 2. So pi goes out this direction, I go out 2. So what I get is something that looks like this and like this. You could try some other values in between, but you know your radii keeps getting smaller as the sine of theta gets bigger. So it starts out at 2 and the radii keep getting smaller. Now when you put in 3 pi over 2, you get 2 times 2 or 4. So 3 pi over 2 goes down this direction, but we go down 4. So we actually get another cardioid, just in a different orientation this time. And we want the area inside the circle and outside the cardioid. So it's this area up here. Well, you can kind of see it from the graph, but if you were trying to see where they intersected, you'd see when the sine of theta equals 0. Because you get 1 minus the sine of theta equals 1, and that's going to be where? At 0 and at pi. So not only does it look like it, but this was at theta equals 0, and this is at theta equals pi. So if I want to draw in my pi, it's going to look something like this. And you can see that pi that we're looking for is right at the end here. So it's the big pi minus the little pi. So we could do it in 2 separate integrals, or we could do it just in one. So 1/2 the integral of r squared d theta. But it's going to be the big radius squared minus the little radius squared d theta. And what angles do we have? From 0 all the way to pi. That's, if you trace out those angles, you're going to get a slice of pi. That last pi is going to be over here. So what's the big radius? The big radius is this circle. So that's going to be 2, and the little radius is 2 times 1 minus the sine of theta. So I'm not going to work this out now. We spent enough time doing antiderivatives and algebra for today. I'm pretty sure that it comes out to be 8 minus pi if you want to practice on that. Instead, I'm going to look at the alternative way that you could do the setup on that. What you could do is to get that in here, is to take the semicircle up at the top. So what's that semicircle going to be? Pi over 2 times the radius squared. And subtract, and what do we have to subtract? We have to subtract 2 of these, and they're the same thing. So I could go 2 times 1/2 the integral of r squared d theta. And for this little one right here, you're only going from 0 to pi over 2. And we're looking at the cardioid now. If you look at that, what we're subtracting off here, those slices of pi would just be in the cardioid. So it'd be 2 times 1 minus the sine of theta. So they both should work out to be 8 minus pi. You can kind of see they look fairly similar. Okay. So anyway, I'll let you work those out. So anyway, that got us through area in polar, which is probably the hardest thing to do. And it'll take a little bit of practice. But tomorrow we'll get into the 2 other things we need to do in calculus, and that is to find slopes in polar and arc length. So we'll see you then.